All right, guys, last question of the set, and this is like the big Mondo question that we have to kind of deal with, and so let's just get into it. So first things first, we have to establish proportionality, right? Um, I'm sorry, this says congruency. That is a typo that hopefully I'll fix before I remember to print this. But this is similarity, and so we have to rely on our two tests, and so our main two tests here are going to be. Hold on, go back. Okay, so are the angles, at least two angles per triangle, congruent, or all the sides going to be proportional? That's really the only two ways we can even prove it. And you know, if we examine this problem, our choices are even more reduced. We only have angles. We don't have enough sides here to actually produce side ratios, and so our only hope of like solving this problem is to prove that all the angles are going to be congruent. Now, the way we're going to do this is to use a dummy numbering system. Like that'd be my encouragement. Kind of like this problem, like where, you know, it didn't really matter what the side lengths were. We just wanted to know the relationship of the side lengths, right? And so we can approach this kind of problem the same exact way. So I'm just going to pick a number for this angle. It doesn't really matter what it is because the angles are not going to affect my side lengths in any way, but I have to try to understand where the angles are and what angles relate to what other angles, right? Um, and so like if this one's 30 degrees, I just kind of fast forwarded here, that one's 30 degrees, that means this angle right here has to be 60 degrees. Okay? And the reason being, we know we have a right angle here, and this is a right triangle, so it has to add to 180 degrees, so 30 plus 60 plus 90, that's going to give me my 180. So continuing on that line of thought, that means this angle here has to be 30 degrees because we're at a 90-degree corner. This much is 60, that much has to be 30. And again, we're dealing with now a small right triangle, making that angle 60 degrees and that angle 90 degrees, right? Now, what's important here is that this shows that all three triangles are indeed similar because all the angles in all three triangles are corresponding and congruent. Now, again, you could be asking yourself this really important question, which is that only true because I chose 30? Well, no, it's not. It's true all the time. Let's say this angle is actually 40 degrees instead of 30 degrees. Well, the relationships don't change, just the angle measurements, right? So if this angle is 40, this angle becomes 50. That means this is 40, and then that's 50. All the angles that were corresponding and congruent beforehand are corresponding and congruent now. So in the same sense that, like, it doesn't matter what numbers you actually pick for this, because you always have to have, like, a half-double relationship, meaning that these other two side lengths will always have a half-double relationship. No matter what angle these angles turn out to actually be, you'll always have this similarity relationship. All right, so why is that important? Well, that's important because that tells us that these triangles are proportional. The side lengths are. So we can write ratios and then we can solve them. Now, the problem here, as you should hopefully be understanding it, is that now the triangles are definitely facing all different directions. Okay? And so trying to pick out what side lengths go with which side lengths is not as easy as it was, say, for this type of problem, like right here. Because once we pulled them apart, it was pretty obvious which sides went to which sides. It is not obvious on this problem. In fact, I would say it's probably the least amount obvious out of all the problems we've worked so far. And so the strategy is going to be to pull these triangles apart. But like, here's the deal. Why don't bother to pull these triangles apart if you're just going to redraw them like this. Okay? And the reason why is not just because it makes a weird face, but like, it doesn't solve the problem of the triangles being like rotated and flipped in weird ways that makes correspondence hard to track. So like if I'm going to go through like the problem of like redrawing them, I want to redraw them so they're all facing the same direction, where all the 90s are in the same place, okay, and then all the 30 quote unquote 30-degree angles are in the same place, right? And so I did that ahead of time just because I know I'm not a good artist with a mouse. And so this is what I'm talking about. Like if we're going to redraw, let's actually redraw it. So like it makes our problem solving parts of this this particular problem way easier, right? Now, to do that, we have to be really careful in how we relabel it, right? So let's just do like this small triangle right here first. Let's take care of this guy, okay? Now, I'm not going to hold you in suspense. By far, the easiest way to do this is to use angles as a locating device, okay? So here's what I mean. So a small triangle, right? Small triangle down here. Notice where the 30-degree angle is and where the 90-degree angle is. So here's my 30, here's my 90. Notice between the 30 and the 90 is a 9 length of a side, right? Between the 30 and the 90, which means this side right here has to be 9. It doesn't matter how it's flipped in the diagram. It matters where it is relative to the angles, because the angles will tell you the truth. So check this out. Notice where the 30 is. Notice where the y is. It's directly across from the 30. So directly across from the 30, that's going to be my y. Across from the 90 is x, right? You can say between the 60 and the 30 is the x. So 60, 30, that means this has to be x. Across from 90 is the x, right? And so like that kind of numbering system or relabeling system is going to make this part, next part of our job way easier. And so take a second and try to relabel it. I'm just going to, there it is. I'm just going to flip to the one I had pre-made where I relabeled it all. So this is what it should look like. So try to label yourself, pause the video, get it down, whatever you need to do, so we can proceed in solving it. Okay? Because like now that we know that the side lengths, what are all the side lengths actually map out, we can actually start picking out ratios to solve, right? Now it's basically turned into one of these problems right here, where we're just trying to find matches, right? So large triangle stuff, small triangle stuff. This one's going to be a little bit like more complicated, only because we have three triangles which we have to deal with. But here's the deal: proportions are just two-part things anyway. So we had to fill up one ratio equal to another ratio. Right? Excuse me. And so what that means is we're only using two triangles at a time, and so we just have to find like the best two triangles to use. Okay, and so like getting into it, like we just have to start making choices. Like what variable do we want to solve for first? Like maybe we want to solve for x, and so I'm solving this x first. Well, I have to relate it to something, right? So I have to pick another triangle, and I have to use the same corresponding side length. So maybe I pick 41. That's nice. It has a number, right? And now I have to go back to my small triangle and find another thing to work with this ratio. Because if I'm going to write this ratio as like x over 41, it needs a corresponding ratio pair so I can cross multiply. So essentially, I'm saying so far that I'm going to ignore this last big triangle. I'm just working with these two because that's where my numbers came from in the first place. And so I need another two set of side lengths. Okay, I cannot introduce new variables, and so I can't use like y and 9 because I can't solve one equation two variables. So that's no good. I can't do that. The problem is I can't use 9 and z either because that also introduces a new variable to the mix here, right? Now, that's no big deal. What that means is maybe I just can't use these two triangles, right? So let me clear the ink here. Let's start over. So I still want to solve for x, but I can solve for x right here, right? And so let's pick a triangle to work with. Well, I can't work with this triangle because it corresponds with y, and that's two variables. But I can use this one. So again, I'm kind of saying, ooh, my screen, where are you? There you are. I'm going to kind of ignore the small triangle right now. I'm just working with these two. Okay, but again, what I need is another set of side lengths, one from each triangle, to match. So I could try 41, but the problem is, oh no, that's y plus z. I could try, oh, not you, 41. Give me the ink, come on. So I could try z, and I could try 41, but again, that brings in too many variables. So again, that doesn't necessarily mean I can't solve the problem. What that probably means is I can't start with x's. But let's see if we can start with y's or something. So like, what if I use y and 9? Well, there's 9 and z. Oh, that's no good. I can't use y plus z because that's already two variables. Well, maybe I can solve for z. Okay, so let's say I'm using z. I'll pair it with 41. 9 and x. Oh, dang, that's not going to work either. Z and 9. Oh, 9 and y. Wait, I have a 41 here. 41 and x. Okay, so it seems to like we've run into a little bit of impasse, right? Because like we have no way to set up ratios that don't have more than one variable in it. And so like again, this is not a point where we should look at this and say, well, there's no way to solve it. We should go back to our original diagram and see if we can actually generate some more information. Because right now it seems like we don't have enough, right? So let's focus in on this diagram. One of these triangles is particularly interesting. It's this triangle right here. Okay? So the reason this triangle is interesting is because it is a right triangle. And unlike the other two right triangles, I actually do have most of the information. This is a triangle in question right here off the main diagram. This might be a little easier to understand what I'm talking about. I have a right triangle, and I have two sides of the right triangle. So what should immediately come to mind? You have a right triangle, you have two of three sides. There's a formula. It's a theorem-based formula that explains how to actually get another side length. So hopefully, or side length, excuse me. So hopefully in your head, you realize what I'm actually referring to. This is just a triangle capped over, is the Pythagorean theorem. Okay? And this is just a sneaky part of real problem solving. Sometimes you have to bring in things that you weren't warned about ahead of time. Pythagorean theorem is something you definitely should carry from previous grades. We've used it this year too. Anytime that your brain thinks about a right triangle with side lengths, you better also immediately start thinking about Pythagorean theorem. I'm starting to realize not everyone's there, which is going to be it tells me what we have to do next unit quite a bit. But this is Pythagorean theorem. Now, what this means is we can actually find z without needing proportions, and that's going to help us actually finish up this problem. Okay, so remember, Pythagorean theorem is a squared, b squared, c squared. The only thing that matters in terms of where you put it is c. C has to be across from the right angle, be the hypotenuse. And so the only thing that we care about is that 41 has to be in the C position, right? And so this could be an appropriate setup for that. The B value in this case is just our Z value. And then of course we have our 9 as one of our side lengths. So we have a squared plus b squared equals c squared, where c squared is going to be 41. Now remember, these are squares, not times 2, so 9 times 9 is 81. 41 squared is 1681. We just have to solve for x, so let's subtract 81 on both sides. So subtract 81 gives you 1600, not 1400. That is a classic typo. Oops. 1600. All right. And then if you square root both sides, to get rid of that square, we're going to have to apply a square. We're going to have to apply a square root. There it is. Apply a square root. And so square root of 1600 is just 40, which means this side has to be 40, which fits because the hypotenuse is the largest side length. That's going to work out. So this side length is just 40. So what that tells us, if we go back to z, the z value is now actually 40. And so that means right here, this side is not z, it's actually 40. And then this is not y plus z, it's y plus 40. Okay, so that actually opens up quite a bit of possibilities for us. And so let's go back to solving for x. That was our original plan anyway. All right, so now that we have x here, I can pair with 41. In the same way I can pair 9 with 40, right? And so since I knew the triangles were proportional anyway, I can now set up and solve for that proportion. And so I can say x is to 41, setting a ratio of small triangle to large triangle, in the same way that small triangle 9 is to 40. Okay? So x is to 41, in the same way 9 is to 40. Right, and so doing a little cross multiplication magic, so 41 times 9 is equal to 40 times x. And divide that by, so we have cross multiplication here. So 40 times x is equal to 41 times 9, 369. And if you know what comes after that, don't say it out loud. Okay, and we divide it by both. We divide 40 on both sides, and we have an x value of 9.255, or 225, excuse me. Okay, and so it's a little bit of a sneaky problem, and so there's a lot of problem in the setup. But even once you get the setup, you kind of have to recognize that you could generate a z value. It's one of those things that's not really a trick after you see it the first time. All right, let's go ahead and solve for y. So let's see y. So let's pick out a y value. That right there. So we can pair that with 9. Okay, so I can do something like 9 is to y, setting a large triangle to small triangle ratio. And we just have to find a pair ratio to work with it. I'm just going to reuse 40 and 9. There's nothing that says I can't. And so just because I used it to solve for x, it's not like it's a expiring kind of thing. So let's cross multiply. So we have 40y this time is equal to 9 times 9, which is 81. So if I take 81 divided by 40, I get 2. So y is equal to 2.025, okay? Which, I mean, if you look at the triangle, is quite small, so I do expect that the values are going to also be quite small. And so, yeah, 2 for the y value. X has to be larger than 9 because it's a hypotenuse, and it is, 9.255. Just slightly smaller, but also 41 is just slightly smaller, or larger, excuse me, than 40, so it kind of works out. All right, a little bit longer problem, guys, but this is, these are all problems that I would definitely know how to do before you took that test. So Please make sure you're working. I should have said this at the beginning of all the videos, but I mean, you have Mr. James. Mr. James is a math teacher, right? So he was working with Miss Rutz in the other part of the building earlier this year. But you're having a math teacher right here in the room. So ask him a bunch of questions. He can answer the questions. It'll be very helpful, I promise, right? So please make sure you're studying. We'll make some big decisions on Thursday when I get back in terms of you're taking the test then or going to wait until the following Monday or Tuesday, excuse me. But that will be your choice on that day. Okay, you guys, good luck on the rest of the day. Sorry I can't be there. I'll see you on Thursday.